This is investigation 58 for curve of best fit. In Algebra 1, we should have been familiar with that phrase, best fit, in finding lines and quadratic models that fit data. In this class, we're going to add to those two things with the potential for an exponential model. So let's start with the idea, though, that no matter what, if we have raw data and we want to see what sort of shape it's taking, we're going to want to look at its graph. In this particular case, it asks us to make a scatter plot using these values as years since 1935. So we're going to go ahead and change these from 1935, that's going to become year 0, and then we'll change each accordingly. So these are the new values we're actually going to use for finding our scatter plot. We're going to be depending on Desmos for this purpose. So you're going to want to open Desmos either on your computer or on your phone. When we look at Desmos, we're going to want to enter the data. To do that, just hit the plus sign to add a table, and then we'll be able to add our values for X and for Y. So you can start typing in your values and fill out the X values up to 35, and then enter the Y values. What you'll notice once you enter the values is that they don't readily show here on the graph due to its scale. So we're going to adjust the scale of the graph using this tool setting, and we're just going to choose the x-axis to go from -5 to 40, and we'll set the y-axis to go from 7,200 to 17,000 in order to make sure we get the lowest value of y as well as the highest value of y. Which looks like I have a typo here. And once we do that, you'll see that the graph does take on a parabolic shape. So when we go to look at question 2, what is the equation for the curve of best fit? We're going to do an equation for a parabola. Desmos does curve of best fit using just typing in the standard form for the equation of a parabola. Make sure that we're going to use x1 for the x variable and y1 for the y variable. That is something Desmos is a little particular about. So we're going to type y1. Since we're doing a model, we're going to use this symbol here, the tilde, in order to do an approximation. And the equation for a quadratic in standard form is ax squared plus bx plus c. Remember that when you type in the x, we're going to type x1. So it's ax1 squared plus bx1 plus c. And once we've got that entered, we'll see both the graph of the parabola show up as well as this information regarding its equation. So we can go ahead and write down the equation using these 3 values for a, b, and c. Question 3 then asks, why do we think this function is a good fit? So a few observations we have. One is the fact that the data goes from larger to smaller and back to larger. The second thing we look at is the fact that when we looked at our graph here, it does in fact have a parabolic shape in general. Not perfect parabola, but at least it is parabolic in nature. And the third thing we look at is this r squared, which is a statistic called the coefficient of determination. It measures just how well a model fits the original data. You can study more about that if you take an AP statistics course. But what we're looking at here is that we want our r squared to be as close to 1 as possible. So 0.2985 is a pretty good indication that this is a good model. So then as we look at number 4, which says, according to this curve of best fit, what is the least number of homicides in the U.S. and when did this number occur? So what we're going to want to look at is the graph and where does this graph bottom out? In other words, where's the location of the vertex down here at the bottom? You can click and drag your graph around, and what we're looking at is this point. If we select the graph itself, a gray point will show up here. We can click on it, and therefore it tells us just the right location. So based on the curve, it looks like the lowest value of y is 6,804, and that it happens at around year 14.14. So we can use that information to say that according to the curve, we've got this to be approximately the least number of homicides. It was down at the bottom of the parabola, and it occurred between 1949 and 1950. Because our value was 14.14 for X, if we add 14 to the year 1935, we would get 1949, but it's a little bit more than that. We can't tell exactly what time of year, so we'll just say that it's between those 2 years. When we talk about the domain and the range of a function, we want to talk about the difference between an algebraic domain and range and then something that might actually happen in real life. Algebraically, this is a parabola, and therefore it's going to have a domain that encompasses all real numbers for x. X could be any value. And the range for this particular function, we said this is about the lowest point here, and so the range would be from that value up. So algebraically, our domain is that x could be any value that's a real number, and our range is going to be greater than or equal to 6,804. That's not the same for what could actually happen in real life. Do we really think that you could go up to infinity with the number of homicides? And the answer hopefully is no. So what we want to do is talk about what's acceptable for a real life domain and range. And there's not one right answer for these. You're going to want to think of a practical idea that makes sense based on the data, but is not necessarily completely based on the algebra that's available. So for example, for the domain, would we really want to use this model to project back into the 1800s? I don't think so. Would we really want to use this model to predict continuously into present day? Again, I'm not sure that would be accurate. So a reasonable answer might be something that goes a little prior to the data you have and a little bit past. So maybe between -5 and 40. And then based on that decision, if you pick somewhere between -5 and 40, we could determine a reasonable range. We've already said that the lowest value of the range algebraically, 6,804. So maybe we go ahead and just call it a round number of 6,800 up to, well, how high could it go? We'd probably project out to one of these values, whichever is higher, to see exactly how high we might accept this projection. So while some things are up to interpretation and allowed to kind of have a little bit of variation in them, the value of the y-intercept for the curve is not one of those things. The y-intercept would be determined by using our equation here and finding where it crosses the y-axis. And as we learned in our last section of graphing, we can do that algebraically by plugging the value of 0 in to find that. Or graphically, Desmos is real nice and will let you just click on that value on the y-axis and go ahead and give it to you. One thing you will notice, Desmos does not always do the same rule as we do. It's set to a certain number of digits. So we are a little bit more flexible in our go to 4 decimal places and truncate in this case. In addition, this particular question is just asking what is that y-intercept? So we would just go ahead and do it to the best of our ability. So we've got our y-intercept, but what does that actually represent in real life? So in real life, we would say 0 is, of course, the year. So we're saying in 1935, the predicted number of homicides would be 10,909 approximately. The y-intercept represents in real life the predicted number of homicides in 1935, which is year 0. A few more things we can get from the graph. What are the zeros of this curve of best fit, and how do we recognize them? Remember that zeros are the same as your x-intercepts. And in this graph, as we saw earlier, it does not cross the x-axis. In fact, it only goes as low as 6,800, so there are no zeros for this particular function. So again, we would say there are no zeros because there are no x-intercepts. Those zeros, should they exist, would represent in the real life would be the years where we would have no homicides. In other words, a graphical 0 is a place where y is equal to 0, and since our y variable is the number of homicides in a given year, that would be the predicted year where there were no homicides. We can use our curve to predict the number of homicides in a specific year. Again, this is not factual information, it's using a model to predict. So if we want to look at 1976, we would see that since 1935, that represents 41 years after 1935. So we would take our x value at 41 and evaluate the function, or plug 41 into the x value of our equation and find that there's approximately 21,620. You can also do this graphically using Desmos. If you select the graph, you can trace it. You can actually trace it right to that value that we have in question, 21,620. We can also estimate to find what year something may have happened. When should 20,000 homicides have occurred? We can do this again both graphically or algebraically. With our tool of Desmos, we can go ahead and add an additional graph of y equals 20,000. And if we find where that happens, we have 2 points, 39.489 for an x value, and we have a second x value on the other side, which is negative 11.21. And keeping in mind that these are our x values, in order to find out what year those are, we would want to take those in relation to the year 1935. And so this is somewhere between 1923 and 1924, and this would be somewhere between 1974 and 1975. As we look at the next example, we're going to again start with a scatter plot of this data. So you're going to want to go back to Desmos and enter in this table of values. And once our data is entered, we again can go ahead and adjust the window so that we can see the values we're interested in. We can go from -1 to 55, and this one looks like we'll go ahead and go from -1 up to, let's go to 20. And so in this particular case, we see this graph is not parabolic because there's no indication that this is necessarily going to turn around and start going back up. So when we see that kind of a pattern, we're going to use an exponential curve of best fit. We still want to go ahead and use the y1 and our approximately, so that it's going to use a model. Exponential curves are a, b to the x1. So remember, in exponential curves, the x variable is the exponent, which is why it calls it an exponential curve. Something we want to set in Desmos is go ahead and click the log mode, and that'll make sure that it gives us the same accurate equation that we would have gotten if we used a TI or another calculator. Like with our quadratic, we want to have two variables here that they give us the numbers for. So we're going to go ahead and report our equation as y equals 15.151 times 0.9570 to the x power. And why did we choose this exponential type of function is that we really had no indication either in the table of values or graphically that this curve was going to start turning around and increasing again in a parabolic fashion. And it's clearly not linear, there's definitely curvature there. To evaluate f of 17, we have two options. You can plug 17 into your function, Or you can go back over to the graph and go ahead and trace until you get the value of 17. And in either case, we'll find that the predicted air pressure at 17,000 feet is approximately 7.189 psi. And finally, like we did with the quadratic model, we can use this to predict x values in addition. So we're going to go ahead back to Desmos and type in an equation of y equals 6. And when we've got that equation typed in, find the point of intersection. Looks like it's at approximately 21.123. So we would say that the predicted altitude where the air pressure is 6 psi is about 21,000 feet. So you're going to want to go ahead and do the practice problems, have fun playing with Desmos, and bring your questions to the group or to office hours if